double quantum, single quantum homonuclear correlation experiment in first mass proton NMR experiment. When we measure the proton double quantum, single quantum correlation experiment, we can obtain this kind of very nice internuclear correlation peaks as well as intense T1 noise along the indirect dimension. This hampers us to use to observe the very small minor peak in this experiment. And the T1 noise is also observed in the heteronuclear correlation experiment like nitrogen-14 proton HMQC experiment. Again, we observe intense T1 noise along the indirect dimension. So, what is T1 noise? And what is the source of T1 noise? It's here. This is the schematic representation of 2D homonuclear correlation experiment. But in the end, we finally observe just an NMR spectrum. Then this NMR spectrum is modulated by the free evolution along in the T1 period. So finally, what we observe is set of the 1D spectrum. Here is one example. We have 1D spectrum, and this intensity is modulated by depending on T1 period. And by applying the Fourier transformation along this axis, we can obtain 2D NMR spectrum. So that means each NMR spectrum observed at different time. So if we have some problem of stability, like instability of NMR equipment for long term, or maybe temperature variation in the course of measurement, we also observe some additional intensity fluctuation. Since time of evolution of T1 period is encoded as intensity evaluation, the T1 and these signal variation introduce additional T1 noise. Then that's why we observe T1 noise along the F1 axis. I mean the peak position in F1 axis. If we don't have any signal, of course we don't have signal variation, and then we don't have any noise. So that's why T1 noise is always appear along T1 axis. And as we discussed, T1 noise comes from fluctuation of signal intensity. That means if you have strong signal, we will obtain large T1 noise. That is, T1 noise is multiplicative noise. In this case, we expect large T1 noise on this signal because of the strong signal intensity. So this is general discussion of T1 noise. In addition to long-term instability, short-term stability is very important in solid-state NMR because of magical sample spinning. This is very regular proton X HMQC experiment. In this experiment, in addition to the regular HMQC block, we also have dipolar recoupling period at excitation and reconversion block. If you look at the proton channel, HMQC is essentially just a spin echo experiment. In order to make the perfect echo at the end of the sequence, we have to apply same Hamiltonian at excitation period and reconversion period as well. Then, if you look at the Hamiltonian, actually Hamiltonian depends on initial rotor phase or gamma angle. So in order to achieve perfect echo, we have to apply sequence exactly at the same timing to the rotor period. So that means these two sequences has to be synchronized to sample spinning. So this is why we need synchronization. However, there is always fluctuation. If you look at the rotor signal 1 millisecond after triggering, you see some small fluctuation of plus minus 0.25 microsecond. This corresponding to 70 kHz spinning frequency with 20 Hz fluctuation. Then, because of this fluctuation, that breaks the symmetry synchronized condition, and that results in additional intensity modulation. That's why this sequence introduce T1 noise due to the spinning fluctuation. This is not a big issue at slow spinning frequency. For example, if we assume the stability of plus minus 0.1% at 10 kHz, that results in 3.6 degree change of rotor phase after 1 millisecond. This is not a big issue. However, with the same level of stability at 100 kHz, that results in 36 degree change of or variation of initial rotor phase. This is big issue, and that introduces the very large signal modulation because of the breaking the synchronous condition. So this is why fast mass proton NMR experiment suffer from huge intense T1 noise. Of course, there is several methods to suppress these problems or alleviate these problems. One of the very practical and very nice experiment is proposed by Fred Peras last year by repeat the experiment very rapidly. It is well known, if we set repetition time with 1.3 times of T1 relaxation time, we can obtain highest signal intensity per unit time. Yes, this is true for direct dimension. The signal intensity is maximized when the repetition time is 1.3 times of T1 relaxation time. This maximized signal intensity, that means this also maximizes the T1 noise as well. Then in the end, the signal to noise ratio in F1 dimension is very low. Then if you reduce the repetition time, that sacrifices the sensitivity, of course. But at the same time, this also suppresses the T1 noise. And since we can measure NMR spectrum very, very rapidly, we can accumulate a lot of spectrum in the same experiment time. And finally, we can improve the sensitivity in the indirect dimension. So this works very well, and this is one of the good practical solutions to suppress T1 noise. Another approach is proposed by Amritz and Aaron Rossini this year. As we discussed, HMQC introduced T1 noise because of the spinning fluctuation. Actually, most of these fluctuation, signal of intensity fluctuation, come from proton chemical shift anisotropy. Then in tone DHMQC experiment, they can apply pi pulse in the middle of decoupling sequence so that proton chemical shift anisotropy is refocused at the end of decoupling sequence. Then this suppresses the T1 noise quite efficiently. In addition to that, we can apply some purge pulse or some spin-off pulse to suppress the signal from uncorrelated peaks. Then finally, in tone HMQC experiment, we have very clean NMR spectrum. This is published this year. This is nice experiment. And similarly, the THMQC experiment can be used. In the THMQC experiment, instead of the proton decoupling, long irradiation is applied to nitrogen-14 to decouple proton nitrogen-14 dipolar coupling. In this experiment, no proton chemical shift anisotropy is introduced, and that gives us clean NMR spectrum without T1 noise. This is also a very nice method to measure proton nitrogen 14 HMQC experiment that is published by Ivan and Zeong last year. So as you can see, there is several methods to suppress T1 noise in HMQC experiment. What about homonuclear correlation experiment, like a double quantum, single quantum correlation experiment? Actually, we have same problem in double quantum experiment as HMQC. This is regular double quantum, single quantum correlation experiment. First, we excite double quantum coherence by some recoupling sequence. Then after free evolution, magnetization is converted by double quantum recoupling. And then finally, we observe NMR signal. Then that is exactly the same story as HMQC. Since Hamiltonian depend on gamma angle, we have to apply excitation pulse and the conversion pulse as a exactly same rotor phase. Or in other words, we need to synchronously apply these pulses to sample spinning. Then again, small spinning fluctuation introduce large T1 noise. This is especially problematic if we have very intense signal. For example, in this case, we have intense message signal intensity. Then regular double quantum, single quantum correlation experiment suffer from T1 noise very largely. Then we face a big difficulty to analyze it. Then we apply very simple solution to it. Just apply very long selective saturation pulse before the measurement to suppress this intense peak. And then finally, we can obtain beautiful NMR spectrum like this. However, this is also not a perfect solution. Obviously, we lose information on CH3, which is suppressed by this saturation pulse. And in addition, T1 noise is still there. But anyway, these T1 noise come from gamma dependence or rotor phase dependence of Hamiltonian. Where these dependence come from? To understand it, we just look at the first order average Hamiltonian that is written here. Then now we are introducing the anisotropic interaction. That means M must not be 0. M has to be plus minus 1 or plus minus 2. Otherwise, M20 term will be 0 at magic angle sample spinning. Then non-zero M term inevitably introduce the gamma dependence. Then that's why Hamiltonian depend on gamma angle in first order average Hamiltonian system. In double quantum, single quantum correlation experiment, that result in spinning sideband in the double quantum dimension. If we measure double quantum, single quantum correlation experiment with a very wide spectral range, in this case, we set 700 kHz, that is 10 times of spinning frequency. We observe many spinning sideband in indirect dimension, that is double quantum dimension. Then in order to improve or in order to avoid problem, we usually set the indirect dimension same as spinning frequency, I mean synchronous to sample spinning. We can fold all the spinning sideband to the center band. But of course, even small fluctuation introduce a change of peak position, and that gives us intense T1 noise. That's why this sequence is sensitive to mass fluctuation. Or in other words, we can look at the picture like this. In time domain, spinning sideband corresponding to the multiple rotor echo at every rotor cycle. Then the excitation pulse and the reconversion pulse must be applied synchronous to sample spinning so that reconversion pulse refocus this at the top of the rotor echoes. Then small fluctuation introduce the large fluctuation of signal intensity, and that results in huge T1 noise. How can we alleviate this problem? One solution could be gamma encoded sequence. In this sequence, signal intensity is cosine modulated. But if we use this kind of Hamiltonian, we can find the helically modulated signal intensity. In this Hamiltonian, actually, size of the Hamiltonian doesn't depend on gamma angle. Only phase of Hamiltonian depend on gamma angle. Then that reduces the dependence to gamma angle, and that also reduces the sensitivity to spinning fluctuation. Actually, this is well known, and we can easily design gamma encoded double quantum sequences. And this table is actually taken from the previous publication. Then there is 4 candidates for proton double quantum decoupling with a reasonable RF field strength. Here is an experimental verification. First, we look at the double quantum dimension with a very wide spectral range. We typically use BABA X516 sequence, which is published about 10 years ago by Kai Sarofsha. And that is beautiful sequence. We have very high filtering efficiency, and we regularly use this sequence. But problem is multiple spinning sideband. If we repeat same experiment many times, because of spinning sideband, signal intensity varies like this. This introduces T1 noise. On the other hand, if you look at the gamma encoded sequence, because of the helical dependence, we only observe single peak at a spinning sideband. Then this gives us much stable signal intensity, even in the presence of spinning fluctuation. In addition to that, this gives us higher filtering efficiency. So from that, we can expect much cleaner NMR spectrum from gamma encoded sequence. This is also verified by numerical simulation. This is experimental verification, the comparison of gamma encoded sequence and BABA sequence. First, you can see the BABA sequence gives us T1 noise, but this noise is suppressed in gamma encoded sequence. This is especially important to look at the signal close to the strong signal intensity, strong peak. In case of BABA experiment, because of the huge T1 noise, this signal is almost suppressed, but we can clearly see it in double quantum gamma encoded sequence. If you look at the slice, this is much clearer. Gamma encoded sequence gives us higher filtering efficiency. That's okay, but this is minor. And noise level in direct dimension is more or less the same. But if you look at the intensity or noise in the indirect dimension, BABA sequences suffer from huge T1 noise because of the gamma dependence, and that is suppressed by gamma encoded sequence. So in terms of sensitivity or signal to noise ratio, we obtain factor of 15 improvement. So gamma encoded double quantum sequence, we don't need rotor synchronization, and because of that, that is robust with respect to the mass fluctuation, and that results in T1 noise. I believe this is the one of the practical solution for double quantum, single quantum correlation experiment. Next, I want to talk about the triple quantum decoupling sequence. In double quantum decoupling sequence, we utilize first order average Hamiltonian, but if we use the double quantum second order average Hamiltonian, we can design 3-spin triple quantum Hamiltonian. Then triple quantum Hamiltonian efficiently excite the triple quantum coherence. And that is suitable for triple quantum without single quantum correlation experiment. Now we are working on second order average Hamiltonian. We already know first order average Hamiltonian inevitably depend on gamma angle when we decouple anisotropic interactions. However, if you look at the second order average Hamiltonian, this is something different. Of course, we have to decouple non-zero M1 and M2, but we can decouple these terms so that M1 plus M2 equal to 0. For example, if we decouple +1 and -1, we can get rid of the dependence to the gamma angle. That is gamma-free Hamiltonian. Then, since Hamiltonian don't depend on the rotor phase, of course, we don't need rotor phase synchronization, and this is robust with respect to T1 noise due to the spinning fluctuation. Fortunately, almost 16 years ago, Matthias Eden already designed the strategy to produce triple quantum decoupling sequence using the second order terms. Then from these 35 solutions, we categorize into gamma-free sequence and gamma-dependent sequence, and we find 5 solutions for gamma-free sequence. Here is an experimental verification. Triple quantum coherence can be excited by double quantum Babbage sequence if that is applied to the transversal magnetization. This is the triple quantum dimension. You can see numerous spinning sideband, and of course that results in the sensitivity to spinning fluctuation. So if we repeat same experiment many times, you can see fluctuation signal intensity, and also this results in T1 noise. Another problem is filtering efficiency very low, only 8%. Low filtering efficiency can be overcome by gamma-dependent triple quantum Hamiltonian. Since triple quantum Hamiltonian directly excites triple quantum coherence, we have much higher filtering efficiency. However, spinning sideband is still there. That introduces sensitivity to spinning fluctuation. But if you look at the gamma-free triple quantum decoupling sequences, peak appear as a center band because Hamiltonian doesn't depend on gamma angle. Then that gives us very high filtering efficiency, 25%. It's almost more or less the same as standard double quantum filtering efficiency. And more importantly, signal intensity is very stable because Hamiltonian doesn't depend on gamma angle. Here is a comparison of gamma-dependent double quantum Babbage sequence that gives us the triple quantum single quantum correlation, and gamma-dependent triple quantum sequence, and the gamma-free sequence. Filtering efficiency is largely improved by triple quantum sequence, but T1 noise is still there because of the gamma dependence, and that is removed by gamma-free sequence. And then we can enjoy high filtering efficiency as well as less T1 noise. If you look at the slice along the indirect dimension, we can clearly see the improvement. As we already know, T1 noise is multiplicative noise. That means highest signal intensity suffer from T1 noise. That's true. The sensitivity SNR in the indirect dimension is much poorer than direct dimension. This is true for both gamma-dependent sequence. However, gamma-free sequence improve the sensitivity a lot. There is still some effect from T1 noise, but that is negligible compared to the gamma-dependent sequence. So, as you can see, gamma-free sequence is solution to avoid T1 noise. Okay, maybe I already spent most of my time, so I just skip the minor point of this presentation. And finally, I want to acknowledge my collaborators. Actually, we start this project during the lockdown. Then because of lockdown, fortunately we have time. Then we started this discussion with Ron Chun-Chan at South China University of Technology and VPN Agarwal at TIFR Hyderabad. And we have a periodic discussion. And in addition to that, I can access my spectrometer remotely. Then we start this project, and finally we have this result on gamma encoded sequence and gamma free Hamiltonians. And then I also thank to the my money source of JSPS funding. And thank you very much for your attention.
Okay, thank you, CK, for an excellent presentation. Now the talk is open for discussion. If you have any questions, please raise your hand. Then you can be selectively unmuted to ask questions. If you have any participants have any question, please raise your hands.
Yeah, I don't see any hand yet.
Okay, I don't think any...
I have a question, but I'm not sure the raise hand feature is really working.
Okay, Amrit. Is it Amrit?
Yes.
Okay, Amrit. Okay, you can ask the question.
Yeah, Nishiyama-san, that was an excellent talk and really nice work. Thank you. I had a question on, can you comment on the MA's dependence? Because most of your experiments were performed at about 70. What do you think about the implications of gamma-free recoupling at about like 40 to 50 kilohertz increase frequency, and conversely, even at higher frequencies up to 100 kilohertz, because there you'll be more limited by the RF fields, right?
Okay, Amrit, thank you very much. Maybe this slide show give us the answer. So one of the problem of gamma-free sequence is that is second order Hamiltonian. So that means second order Hamiltonian is inversely proportional to sample spinning. So if we have higher spinning frequency, we have much smaller Hamiltonian. This is one of the potential problem. In order to evaluate it, we observe filtering efficiency, tube quantum filtering efficiency at several different spinning frequencies from 70 kHz to 30 kHz. Then, as you can see, the filtering efficiency is maximized at highest spinning frequency. That means at least up to 70 kHz, the Hamiltonian, second order Hamiltonian is large enough to produce tube quantum coherence. Then, if we increase further, maybe 100 kHz or 150 kHz, maybe we will suffer from small second order dipole coupling. This we have to think about it. We didn't try faster spinning frequency than 70 kHz, so I don't have an answer at this moment. But at least up to 70 kHz, faster the better.
Thank you.
Okay. Yes, any other question? Anybody has? Okay, if there are no other questions, let us thank Yusuke for an excellent presentation. Thank you, Yusuke. Okay, we'll go to the next talk. As you all know, that because Bikash had some issues in sharing his screen, we took second talk first. Now Bikash is going to give his presentation. Bikash, are you there?
So I'm sharing because your screen, your slides. So basically, you can go ahead if it works for you. Okay. So you can see your slides on the screen.
We can see the slide now. Who is presenting? Bikash is going to present. Okay.
Yeah, Bikash will present, but this is Vivek sir. I'm projecting his.
Okay. Yeah, I know there was some issue in his slide sharing.
Correct,
Okay,
yes.
continue. Now I'm going to introduce Bikash. Of course, Dr. Bikash is currently associate professor working at Center of Biomedical Research, Lucknow. He did his PhD in NMR spectroscopy, of course, from this lab, NMR Research Center, IISc, in 2008. Then he did his postdoctoral work at EPFL, Switzerland, and then at Weizmann Institute, Israel. And from 2014 onwards, he has been working as a faculty at Center of Biomedical Research, Lucknow, and currently working as solution NMR methodology and NMR-based metabolomics. He has more than 35 publications to date, published in international peer-reviewed journals with a H index of 15 and I-10 index of 19. He has delivered invited lectures in various national and international conferences. He has developed many solution NMR methodologies for complex mixtures and biofluids in recent years. So now it's over to you, Bikash. You have 30 minutes from now. Please take 25 minutes and leave 5 minutes for discussion. Bikash, over to you. Bikash, are you there?
Because you need to unmute yourself and then go ahead.
Okay, can you hear me?
Yes.
We can hear you. Please go ahead.
Okay, thank you, sir, for your kind introduction. And good evening to you all. Hope all of you are in good health and spirit during this COVID-19 crisis. I thank the organizers for giving me this great opportunity. And this is my today's topic, unscrambling the complex spectra of small molecules, mixtures, and biofluids by using ultra-high resolution NMR methods. And this talk is dedicated to Professor Atria. And we lost this great soul this year, and this is a very big loss for our Indian NMR community. So I dedicate this talk to Professor Atria. Next. So here are some examples of complex proton NMR spectra I'm showing you. And the first one you can see the human urine, complex spectrum from human urine, the large number of signals with proton multiplets, and there's several spectral overlap. Then the below one is the proton NMR spectrum from a mixture of 9 aromatic compounds. And third one is the small region of the proton NMR spectrum from beta estradiol. You can see there's significant signal overlap in this kind of complex spectra, and there is a need to simplify the analysis of this kind of complex spectrum. I am hearing some voice in the background. Okay.
Participant,
Next.
please mute your this thing. I'm sorry for interruption. Please mute your mics. Because please continue.
Okay. Next slide, please. Next slide. Okay, thank you. Yeah. So there is significant methodological development as well as high field magnet development. The high field magnet development has improved the resolution by a factor of 2 in 3 decades. You can see from 1980s 500 megahertz to 1.2 gigahertz in 2019. And there's a factor of 2 improvement in resolution over 3 decades. But the ultra high resolution NMR or pure shift NMR, this is the pure shift NMR spectrum that the bottommost, and there's a regular proton NMR spectrum. You can see the resolution is very high in ultra high resolution NMR, and they have raised resolution by more than an order of magnitude in less than a decade. Next slide. Okay. So there are 3 terms that is used in this literature: ultra high resolution spectrum, pure shift proton spectrum, or broadband homodecoupled spectrum, or BBHT spectrum. All these 3 terms that I'll be using are more or less the similar meaning. Next. Now there are various ways to get ultra high resolution or pure shift proton spectrum, and there's 4 blocks which are very common nowadays. The BART, first one is BART, bilinear rotation decoupling. This uses the 1.1% photon signals attached to 13C. And the second one is the Zegner and Stark sequence that uses a selective refocusing pulse in the presence of a gradient. The third one is the band selective homonuclear decoupling, suitable for peptides and proteins, where, for example, the H-alpha can be decoupled from the side chain and the amide protons. And the third one is pure shift yielded by chirp excitation, as this one is relatively new. And here we use a pair of small flip angle chirp pulses in the presence of gradient to get a broadband homodecoupled spectrum. Though All this band selective is a band selective pure shift spectrum. This produces the Baird and Zenger-Stark and the Psyche. All these three techniques produces broadband harmonic coupled spectrum or pure shift spectrum, broadband pure shift spectrum. Okay, next. And next slide. So how do we get a pure shift FID? For example, if this is the pure shift FID in the middle of the slide, there are two ways to get this pure shift FID. The first one on the left is the real-time single scan approach. And here the FID is periodically interrupted by the application of this active spin refocusing block. Active spin refocusing blocks are nothing but either the Baird block or Zenger-Stark block or the band selective harmonic coupled block. So this is the real-time or single scan approach, the first one. And the 180-degree hard pulse is used in addition to the active spin refocusing block, so that chemical shift evolution continues and the J coupling is refocused in the middle of this FID. That means this is just small data sign you can see. The other approach is the interferogram-based approach. Here what is done, a series of FIDs of 20 milliseconds duration needs are recorded from a series of pseudo 2D kind of experiments in such a way that the scalar coupling refocuses at the middle of each block, each of this 20 millisecond block. At the middle of each of this block, the scalar coupling is refocused, but the chemical shift evolution is refocused only at the start of the block. And all of these data sinks of 20 milliseconds duration, around 50 blocks of this 20 milliseconds duration, are concatenated to form a synthetic FID, which is called the pure shift FID. And if this is Fourier transform, one can get a broadband harmonic coupled spectrum. Next. And this is the first single shot approach, single shot Baird scheme for producing broadband harmonic coupled pure shift spectrum. And this is reported from the Friedman's groups. And it is a very nice application. Then go to next slide. So this is the Zenger and Stark method, and this is the pulse sequence for the real-time Zenger and Stark. This is on the right side, you can see that broadband harmonic coupled photon spectrum. And at the top of that is the regular photon spectrum. The multiplets are very nicely result into singlets. Next. The third one, this is a band selective technique. It produces a pure shift spectrum in the band selective manner. The broadband pure shift spectrum cannot be obtained by this technique. It produces it utilizes as active spin refocusing block, the band selective refocusing pulse. And here's the example of the proton spectrum at the bottom, and you can see the H alpha band selective pure shift spectrum in this region, and you can see the amide region or band selective harmonic coupling produces the band selective pure shift spectrum. Next. And the fourth one is the Psyche. This is the most sensitive among all the broadband harmonic decoupling technique, except the band selective technique. The band selective technique is the highest sensitive, but it is not broadband. But Psyche, Baird, and Zenger are broadband technique. The Psyche has superior sensitivity compared to the Baird or the Zenger and Stark method. So it utilizes a pair of shear pulses, small spindle shear pulses in the presence of gradient. Here is the spectrum I'm showing you. At the topmost spectrum is a regular proton spectrum, and then immediately below that is the ultra high result proton spectrum from Psyche. Next. The problem with all this pure shift or ultra high result NMR is that it does not provide the decoupling information. They provide ultra high chemical shift result information. They don't provide ultra high result multiplet information. So in fact, the Z-result NMR is the only experiment that provides both the chemical shift and scalar coupling information, but at much lower resolution. If we look at, for example, this is the Z-result spectrum, and the direct dimension of this tilted Z-result spectrum provides us a pure shift spectrum. You can look at the F2 projection, and this is a very low resolution pure shift spectrum. And if we look at the indirect dimension, these are the multiplet information, but there are a lot of line broadening and phase distortions because the dispersive terms are intrinsic to the Z-result spectrum. And till that there is not an ideal solution to overcome this phase problem in the Z-result spectrum. Next. So I'm showing you the proton spectrum at the topmost, the proton spectrum of S-binol, and then immediately below that is the proton pure shift spectrum. So this is the chemical shift information. We don't get the scalar coupling information from the pure shift spectrum, but scalar coupling information is crucial for structural elucidation of molecule. This is a very important piece of information. And the current Z-result spectroscopy does not give us a very high, well-resolved pure shift spectrum. If we could get a spectrum like this on the right side, this is also a pure shift spectrum, Z-result spectrum, but the resolution of such Z-result spectrum is very high. The direct dimension of this Z-result spectrum is a very high, well-resolved pure shift photon spectrum. You can see the regular Z-result spectrum cannot give this kind of pure shift Z-result spectrum in the direct dimension. And in the indirect dimension, we have the ultra high result multiplet information, but that is not possible with using the regular Z-result spectroscopy. Next. So this is the basis of our experiment. Initially, I focused on how to get an ultra high result Z-result NMR using the pure shift approaches. So the first technique that I developed was the real-time band selective homodecoupled Z-result spectroscopy. So here I'm showing you at the left side, there's a regular Z-result spectrum. The lines are very broad due to the presence of dispersive terms. This is a typical spectrum. So there exists a way to remove these dispersive terms that was reported by the group from the group of Buchard-Loy around 2009. This is you can see the pulse sequence that filters Z-result spectrum. So using this pulse sequence, it is possible to get rid of the dispersive terms, and you can get the second spectrum in the middle, absorptive mode J spectrum with full multiplet information. The Z filter removes the dispersive terms and signals becomes very narrow. You can see in the middle spectrum, the signals are very narrow, but it introduces another problem. The multiplet information are present in the direct dimension as well. So the multiplet information is present in the indirect dimensional, and it is also present in the direct dimension, and this together leads to lack of resolution for this kind of absorptive mode Z-result spectrum. And we figured out that if we apply the real-time BBHD blocks like bilinear rotation decoupling or Zagara-Stark sequences or even band selective sequences, if we apply the real-time application of these pure shift approaches, then it is possible to get ultra-high result Z-result spectrum that I have shown on the right side. Because the moment we apply these real-time broadband homodecoupling blocks, the multiplets and the direct dimension of absorptive mode Z-result spectrum can be replaced by singlets. And so we designed this sequence, real-time band selective homodecoupled Z-result sequence. Next slide. So you can see the FID is periodically interrupted by the application of the band selective homodecoupling block, and the indirect dimension is the Z filter Z-result pulse sequence. Next. So using this, we can get very nice, well-resolved spectrum. The left is on the left side, you can see for this molecule glucose individual, and this is the Z filter Z-result spectrum. This is the absorptive mode Z-result spectrum on the left. Here the lines are narrow, but the multiples are present in both dimensions, and therefore this leads to overlapping of signals. But if we go to the real-time vast decoupled Z-result spectrum, ultra-high result Z-result spectrum, you can see that this overlap of signals in the direct dimension can be overcome, and we can extract these informations in a very convenient way. Next. Okay, there is another technique that after publishing this work, we saw another technique in the literature from the group of Professor Gareth Morris group, and they used the psyche, which is a broadband, which produces a broadband pure shift spectrum. They used the psyche block, which they result in a MAR, and you can see a very well resolved ultra high result Z-result spectrum. Next. So this is another technique. So we did real-time band selective homodecoupling, and we made this technique broadband using the bilinear rotation decoupling during the real time. Next. Okay, you can go to the next slide. So this is the pulse sequence we have applied. You can see the real-time bilinear rotation decoupling block during FID acquisition, and we have replaced the multiplets by singlets. The indirect dimension is still the Z filter Z result NMR, but the signals in this sequence are the 1.1% protons attached to 13C. The sensitivity is less, but the resolution of this kind of spectrum is very high. So I'll show you an example of spectrum. Go to the next slide. So we took a red cortex tissue extract samples, and you can see the top 3 spectral portions are from the regular Z result spectrum, and the bottom 3 are from the real-time Barr decoupled absorptive Z spectrum. A small portion, for example, panel C, you can see the portion marked with level P. The line broadening and phase distortions induced by the dispersive signals are very high. It is very difficult to extract the scalar couplings or multiplet information from this kind of magnitude mode regular Z result spectrum. But if you compare this portion C with portion D, you can see in real-time Barr decoupled absorptive Z spectroscopy, it is very well result. In fact, we can say that these are ultra high result multiplet information in the indirect dimension, and the direct dimension will be ultra high result pure shift spectrum. So the line narrowing can be achieved from the panel E and F. Also, you can see that real-time Barr spectrum provides very nice line narrowing with very well result multiplet information. Next. So some other spectral portion you can see it in the regular Z result experiment in 4E, the GABA signals, the multiplet from the gamma is overlapped with is distorted by the singlets from the creatine, but in the ultra high result or real-time Barr absorptive mode J spectrum in 4F, you can see the line becomes very narrow and the pentatom GABA is very well resolved. So this kind of ultra high resolution can be achieved using the Barr block in the direct dimension of the result spectrum. Next. Then another technique we figured out while doing this work, how to improve the Z results, how to improve the resolution of the result spectroscopy for biological complex mixers such as human urine. So this is the technique using double quantum filter, and we call it double quantum filter Z result spectroscopy. Next. So I'll show you here. On the left, you can see there is a double quantum filter. So if we have two coupled signals, HA and HM, and we apply double quantum filter, then these two coupled signals pass through the double quantum filter. But if there is a very intense singlet peak or single non-coupled signals, so single non-coupled signals does not go through the double quantum filter. And using this simple trick, it is very easy. It can be shown that the resolution of the regular Z result spectrum can be improved using double quantum filter Z result spectrum. So for example, in this regular Z result spectrum on the left, you can see there is a very high intense singlet along the line A. And the multiplet information near this singlet is like obscured. Now in the double quantum filter Z result spectrum, this singlet signal is drastically reduced. And you can see the multiplets along the line A prime and B prime are very well resolved. Okay, next. So here I am showing you the projections of, for example, the first one is the proton NMR with pre-saturation for a lyophilized human urine sample from D2. And you can see that the creatinine singlets are very high in intensity marked with star. These two star marked signals are the creatinine singlets. They are very high in intensity. Now, if we take the projections of a regular Z result spectrum, and it is still dominated by these creatinine singlet signals. The multiplets informations, if you look at both sides, the multiplets from the weak intensity multiplets are not properly visible because the receiver gets saturated with the signals of these singlet signals. Now, if we go to the projections, and the third one is the projection of double quantum filter Z result spectrum, the intensity of these singlet signals are drastically reduced, and you can see the low intensity multiplets on either side of the spectrum are very much visible. So this is the pulse sequence at the bottom, and the Z result sequence is basically preceded by a double quantum filter. Next. So here is an example. You can see the two spectrum E and F in the bottom. So there's a very intense singlet signal in the spectrum E, and there's a multiplet signal termed with phi, marked with phi, and this multiplet signal is not very much visible. But the moment we go to the double quantum filter Z result spectrum F, And you can see this multiplet information. This multiplet becomes very much visible as soon as we suppress the intense singlet from the acetyl aceton. Next. Then here is the, okay, here are the spectra recorded on human urine. So portions of the Z result spectrum, and on the right side is the portions of the double quantum filter of the result spectrum. You can see that the intense singlet on a Z result spectrum can be very nicely suppressed using the double quantum filter of Z result spectrum. Many multiplets can be very well resolved. For example, all the three spectra demonstrates that the singlet signals can be very effectively suppressed, and the weak intensity multiplets are properly visible in the double quantum filter of the result spectrum. So this is another way of getting high resolution. We just suppress the very intense singlet signals in biological complex mixtures like human urine, and then the multiplet informations of the weak intensity multiplets are readily available from this kind of double quantum filter of the result spectroscopy. Next. This is another application on medicinal plant dried fruit extract, Z-pedancolata dried fruit extract from Northeast India. You can see the first spectrum, regular Z result spectrum marked A, there are 3 intense singlets. The moment we suppress these 3 intense singlets on spectrum B, you can see double quantum filter Z result spectrum, that triplets, there are many multiplet information becomes visible. So similarly, it can be shown for other peaks in the spectrum shown below. Next. So these were the Z results experiment, and we got very ultra high resolution Z results spectrum using these techniques, and the real-time application of BARD or band selective homodic coupling, or even the application of multiple quantum filters during Z result experiment can drastically improve the resolution of the spectrum, particularly for complex mixers. Another technique that we developed is the pass soft koji, parallel soft koji. Here I am showing you. Okay, you can see that Zenger and Stark methods can be used for obtaining broadband homodic-coupled pure set proton spectrum. Then around 2010, Professor Dennis Marlett group showed that it is possible to record Z-surf spectrum. Z-surf spectrum actually we record parallelly many surf spectrum. And what is a surf spectrum? Surf spectrum is is a way to get a site-specific measurement of Z-coupling interaction between any two spins that are coupled. So it has to be performed like 2 spins at a time. But this procedure can be parallelized using the Z-surf sequence. And what the Z-surf does is the slice selective excitation, and then slice selective refocusing in the middle of the sequence, and then the slice selective storage of all these signals which are coupled to a particular proton spin. And we found that there is another way of recording this kind of spectrum, and that is the parallel soft koji spectrum. What we did is a slice selective mixing. So instead of this slice selective excitation, refocusing, and storage, one can resort to slice selective mixing for recording parallel soft koji spectra, analogous to Z-surf, which is also a parallel mode of acquiring surf spectra. We can do the parallel acquiring of soft koji spectra. Next. So here are the pulse sequences. You can see the bottom one is the soft koji spectrum. What we do here, the first 2 pulses, selective pulses, are applied on spin 1, and the third pulse with phase phi are applied on spin 2 for recording 1-2 soft koji, or it is applied on spin 3 for recording 1-3 soft koji spectrum. So 2 experiments have to be performed. And the topmost in the past soft koji pulse sequence, you can see that the first 2 is still applied. The first 2 selective pulses, 90-degree pulses, are still applied on spin 1. The third selective 90-degree pulse with phase phi 3 is applied in the presence of gradient, and this does the spatially selective coherence transfer. So if we have 3 spectrum like this in the presence of gradient, then this 90-degree slice selective coherence transfer pulse, the third pulse is the slice selective coherence transfer pulse, selectively transfers the coherence from I1 to I2 in a separate slice B, and I1 to I3 coherence transfer takes place in another slice C. And this preserves the spin state selection that is the center of, that is the main focus of soft koji kind of spectrum. So in one experiment, one can record multiple soft koji spectrum. Next. Here's an example, and this is the past soft codis S1B in the top. This is the past soft codis spectrum of the protons HA and like 20A and 11B protons of the sample strychnine. So you can see there are 3 soft codis spectra that can be recorded parallelly using this past soft codis approach. And each of these soft codis spectra are now shown expanded in the bottom portions of this figure, and there are reduced multiplets akin to similar to the soft codis spectra. So we can extract both active as well as passive coupling informations from this kind of soft codis spectra, and the procedure can be parallelized, which leads to reduction in experimental time. One important point to note here is that the lines are antiphase, and therefore if there are very small couplings, then there may be cancellation of the signals, and that is a drawback of past soft codis kind of spectrum. Okay, next. This is another example on a sample of hesperidine. We could very nicely simplify the soft codis multiplets, soft codis cross peaks, and the 2 relative configurational isomers of hesperidine could be well resolved using this past soft codis spectrum. So here a little bit about the G-SURF, and you can see there I'm showing you a G-SURF spectrum on the right side, spectrum C. And G-SURF provides only active coupling information. Signals are in phase, and therefore there is no cancellation for small couplings. That's the advantage of G-SURF experiment. The drawback of G-SURF experiment is there are strong axial peaks along the frequency line 0. At the 0 frequency along F1 dimension, you can see very strong intense singlets. And it provides a very nice site-specific measurement of the couplings. For example, the coupling between 15B and 15A is measured at the chemical site of 15A, and similarly between 15B and 16 is measured at the respective chemical shift of 16. But the problem is the axial peaks, and actually there is a way to get rid of these axial peaks, and this is a clean G-SURF developed from the group of Professor Suryaprakash. And you can see that using clean G-SURF, one can overcome these axial peaks. This is the regular G-SURF, which is dominated by axial peaks. And at the bottommost, you can see that the clean G-SURF is very robust for the measurement of this kind of smaller couplings. So these are some other techniques developed from other group. Then we went for developing another technique for identification of metabolites in a plant metabolomic sample coriander seeds, and this is an application of F1 cytotoxic spectra experiment developed by Professor Morris group. Next. So regular regular toxic spectrum can suffer from significant spectral overlap. You can see at the bottom regular toxic spectrum on the left side from a molecule like beta estradiol, and you can see that the signal overlap can be very significant for certain reasons. And this problem becomes even more exaggerated for when you go for metabolomic complex mixers. So what we thought, we evaluated the 2D F1 cytotoxic experiment for metabolomic complex mixers. You can see that in the middle spectrum is the 2D F1 cytotoxic spectrum. So the pure shift spectrum can be obtained in the indirect dimension, and therefore it has an order of magnitude high resolution compared to the regular toxic experiment. And we immediately applied this F1 cytotoxic experiment to metabolomic sample. Next. And we applied this to an aqueous acetonitrate extract of coriander seeds. You can see the regular potent spectrum, and various regions are expanded. There is significant amount of signal overlap. And this can be like solved by using various two-dimensional technique, HSQC, Toxi, J result. And in this toolbox, we also included the Psychitoxi experiment, because Psychitoxi gives much higher resolution than regular Toxi. The Toxi is very important for metabolomic complex mixer, because the spin system identification can be performed very conveniently and by Toxi experiment. We use the BMRB, HMDB, metabolome, datamase, Cannomics, NMRS suite, and using all these techniques, we perform the analysis of the metabolites, identification of the metabolites. Next. So here I am showing you the application of F1 cytotoxin. On the left side is the F1 cytotoxic spectrum, and the right side is the regular toxic spectrum. You can see there's a tremendous signal overlap in the regular toxic spectrum from coriander seed extract samples, but on the left side, F1 cytotoxis provides very well reserved ultra high result pure shift spectrum in the indirect dimension, and you can see the resolution is very high. We could identify 36 pin systems and 36 metabolites using this pure shift toxi, but using the regular toxi, due to the signal of overlap, we could not go beyond 27 metabolites. So we could confirm 9 more metabolites using the cytotoxi. In fact, many other peaks are very well result in cytotoxi, although we could not make the assignment. But spin system identification of more than 36 metabolites could be performed using F1 cytotoxi. Okay, next. So these are the some of the sections expanded. You can see on the left side, very high resolution spectrum. On the right side, a lot of overlap with the regular toxi. So this is how we could assign the metabolites more conveniently using F1 cytotoxi experiment. Next. So another technique that we developed was the diagonal suppressed F1 BART toxi. So similar to cytotoxi, we developed this, we applied this BART along the F1 dimension of toxi experiment along with the suppression of the diagonal peaks. I'll show you how this technique helps in assignment of signals in complex spectra. Okay, next, we can skip this. Next. This is the pulse sequence for diagonal suppressed F1 BART toxi. And what we do, at the center of T1 evolution period, there is a BART block and the signal is again filtered through in-app transfer. The 1.1% photon signal attached to 13C is selected. Then F1 dimension is broadband homodecoupled using the BART. And when the signal goes to the direct dimension, there's a multiple quantum filter. We found that the diagonal signals in toxi in this kind of experiment are the magnetization that is attached to directly attached to 13C. The proton signals that is directly attached to 13C, whereas the cross peaks are the magnetization which are actually attached to carbon-12. So these one can use a multiple quantum filter to suppress the diagonal. Here is an example I'm showing you on a mixture of 9 aromatic compounds. So this aromatic region, you can see in the regular toxi, there is a diagonal, there are diagonal peaks and there are cross peaks, but the multiplet information in both dimensions can hinder assignment. And if you go to the right side, the diagonal suppressed F1 BART toxi, the diagonal is immediately suppressed. There is no diagonal in the spectrum. And F1 dimension, indirect dimension is the pure shift to broadband homodecoupled spectrum. And therefore the resolution improves drastically in this kind of diagonal suppressed F1 BART toxi. Next. Here I am showing you the comparison of all the three techniques, the diagonal suppressed F1 BART toxi, and in the middle is the regular toxi, and at the end is the F1 cytotoxi spectrum. You can see that the F1 cytotoxi as well as the F1 BART toxi, both are better than the regular toxi experiment because the multiplets are replaced by singlets in the indirect dimension in both BART toxi as well as cytotoxi. But the BART toxi performs better than cytotoxi for this kind of aromatic mixture because the diagonal is absent in the BART toxi. So the particularly the two signals, one marked with 1 and 2 in BART toxi is very clearly resolved, but these two peaks which are close to the diagonal in the cytotoxi, they are not much resolved. Further, the BART block does not need much optimization like F1 psyche blocks, and therefore there are a lot of advantages in using diagonal suppressed F1 BART toxi for complex mixers. Next. So these were also applied on a mixture of carbohydrates. So you can see from the comparison of the two spectra, the diagonal is absent in the diagonal suppressed F1 BART toxi on the right, and the multiplets which are like overlapped on the left are well resolved along F1 dimension. For example, the xylose glucose or the alpha glucose, beta glucose signals are very well resolved on F1 BART toxi, but they are not properly resolved in the regular toxi experiment. Next. Then now I'm coming to the last topic. I hope I have another 5 minutes. You can see pure shift HMQC. This is a technique that we developed I think early this year. And how to improve the resolution and sensitivity using bilinear rotation decoupling in the indirect and direct dimensions. Go next. So here is a comparison of a cross peak of HSQC and HMQC. On the left is a HSQC cross peak. And on the right is the cross peak from the HMQC experiment. So if you look at the F1 dimension of HSQC, all peaks are singlet at the respective 13C chemical site. But if you look at the F1 dimension of HMQC, the peaks are multiplied along F1. So both spectrum has multiplied along F2 dimensions. So recently, using this Bayard-based real-time broadband homodecoupling from Professor Murray's group, they have shown that in HSQC, this multiplied along direct dimension can be reduced to singlet, shown below. So you can see the pure shift HSQC cross peak in the below spectrum. So this is obtained when we apply a real-time broadband homodecoupling in the direct dimension of HSQC using Bayard blocks. If we do the same thing with the pure shift HMQC, if we do the same thing with HMQC, then we'll be able to do a multiplied reduction in the direct dimension in HMQC also, if we apply these Bayard blocks in the direct dimensions. But then indirect dimension is still a multiplied. In fact, this is a very long-standing problem in NMR. If you look at the textbooks of NMR, that in HMQC, if we do under high resolution, it always shows the multiplied information in the indirect dimensions, which reduces the resolution as well as sensitivity of HMQC. And that's why HMQC is not very much preferred compared to HSQC. But there's a way to solve this problem. The problem is with HMQC is that the proton-carbon multiple quantum evolves under the proton-proton coupling interactions, and therefore the indirect dimension shows the proton-proton multiplet information. And if one could think that one can apply a Bayard block in the middle of the T1 dimension, this is the HMQC pulse sequence, and if we apply a Bayard block at the middle of this T1 dimension, it does not work because Bayard has this fundamental requirement of proton-carbon interaction. The proton or carbon coherence has to evolve under the one-bond proton-carbon couplings. But the proton-carbon multiple quantum coherence does not evolve under the direct proton-carbon scalar couplings, and therefore Bayard cannot be applied in the middle of an HMQC pulse sequence. But there is another way to solve that. We developed this pure shift HMQC pulse sequence. And what we did, instead of applying the Bayard at the middle of the HMQC block, HMQC T1 evolution period, since Bayard cannot be applied here, this multiple quantum evolution period can be preceded by a Bayard block, and which is preceded by a single quantum evolution period. Now, if the single quantum evolution time period is matched to this multiple quantum evolution time period, then this broadband homodecoupling block, what it does, it refocuses the evolution of proton-proton scalar couplings in the indirect dimension. So it is possible to get rid of the proton-proton J evolution in the indirect dimension of HMQC using this very clever trick. And direct dimension, it is always straightforward to apply the Bayard block using the real-time or single shot scheme. And here is a comparison of the spectrum. You can see the cross sections extracted at the HMQC. You can see there are phase problems. Actually, the evolution of proton-proton scalar coupling can also introduce phase problem in the regular HMQC spectrum. There are multiplied informations as well as the phase problems in the regular HMQC cross peaks. And now if we go to the pure shift HMQC cross peaks, and then we can see that the multiplets are reduced to singlets in either dimension, F1 as well as F2. And then we also compare this with the pure shift HSQC of Professor Murray's group, reported by Professor Murray's group. And you can see that the pure shift HMQC is almost equivalent to pure shift HSQC. Next. There is a comparison on glucose of all the three experiments, regular HMQC, pure shift HMQC, and pure shift HSQC. If you look at on the cross section A, you can see in the regular HMQC there is distortion of the spectrum. And if you go to pure shift HMQC in A prime, the cross sections A prime, you can see there are two carbon chemical shifts which are well resolved. And the same can be obtained in the pure shift HSQC cross section A double prime. But if there are geminal protons, then the pure shift HMQC cannot decouple this geminal interaction in the indirect dimension. And therefore, if there are two geminal protons shown which cross section B in regular HMQC, you can see the signals are distorted. And pure shift HMQC cannot decouple this geminal interaction in the indirect dimension, and there are phase problems for geminal protons. But pure shift HSQC can resolve if you look at the cross section B double prime. So for geminal protons, pure shift HSQC is still better than pure shift HMQC, but otherwise the performance of pure shift HMQC and pure HMQC are same. Next. So here's a comparison of the sensitivity of all the three experiments. You can see that the regular HMQC gives multiplex, and the pure shift HMQC gives singlets in the middle, and you can see the enhancement factors 1.8, 2.1 compared to the regular HMQC, and then there is pure shift HSQC provides enhancement factors of 2.2 and 2.5 for the signals. And for routine work of T1 acquisition times, the pure shift HMQC and pure shift HSQC have same sensitivity and resolution. From the comparison of this like enhancement factors, you can see. Now I'll skip all these things, and
Bikash, can you summarize, Bikash?
Yes, yes. Okay, next. So here's the summary. So we have shown that it is possible to improve the resolution of complex proton NMR spectra using pure shift or ultra high resolution approaches. We could demonstrate that various new NMR methodologies. We demonstrated that ultra high resolution spectroscopy using pure shift approaches on complex samples such as red cortex tissue extract samples. We demonstrated that a double quantum filter visual spectroscopy provides very high resolution spectrum from biofluid samples like human urine. We demonstrated parallelly acquired slice selective soft Koji spectra. We demonstrated diagonal suppressed F1 bar toxic experiments for aromatic mixers. And we also developed this pure shift HMQC techniques. We also developed application of F1 cytotoxic experiments for plant metabolomic samples. Next, and acknowledgement. I acknowledge my students Ajay, Upen, and Rasmi, and collaborator Dr. Nilamani Nath from Guwahati University. I acknowledge Center of Biomedical Research for NMR facility and Department of Science and Technology India for extramural research fund. And next, lastly, I thank you for your kind attention. Thank you.
Okay, thank you, Bikash, for an excellent work and also excellent presentation. You've done a lot of work.
Thank you, sir.
Now the talk is open for discussion. Please raise your hands and then we can selectively unmute. Any questions? Anybody has any questions? Looks like that it is a crystal clear talk. No questions are there. Okay, with this, if there are no questions, let us thank Bikash. And I would like to take this opportunity to thank both the speakers of the day, Yusuke and also Bikash. And of course, as you know, this change of timing was because of the talk from Yusuke. Otherwise, would have disturbed in the middle of the night. So that's why we little bit preponed for the day. It is only for today. From next week onwards, again, we'll go back to our scheduled time of 7:30 in the evening. So with this, I'll thank the speakers and we'll call it a day, and we'll meet you again next week. Thank you all.
So you may want to speaker, poster.
Okay, I'm sorry. I would like to show the speaker of the next week. Okay. So next week we have two speakers. One is Professor Mahavir Singh from IISc and Professor Sujit Bhattacharya from NTU. So that I look forward to these exciting talks next week. We'll meet again next week. Is there anything you want to add, Vivek?
No, that's all. Thank you, sir.
Okay, thank you very much. We'll meet again next week.
Okay, thank you, everyone. Bye.
Thank you. Bye-bye.
Yeah.